We've got a few things to go through today. The first is I just want to go over molar mass of a gas. Um, just like molar mass of anything else, it equals grams per mole. Um, you could also write it as moles equals grams over molar mass. And then if you look at your AP chemistry reference tables, for some reason, they decide to use N equals M over M, where they use a lowercase m for grams and a capital bold italicized M for molar mass. But if you look over on the right-hand side of your reference tables, they tell you what all those things mean. The next thing I'm going to do is go through a few of these concept check questions. And as you go through them, I'd like you to pause the video, think of your answer to the question, and then listen as I go over the answers. So pause, think, and then continue. You're going to want to have a periodic table handy to refer to as well. So first one says, you're holding two balloons of the same volume. One contains helium, one contains hydrogen. Complete each of the following statements with different or the same and be prepared to justify your answer. So the pressures of the gas in the two balloons are, think of your answer. The answer is the same because in each of these balloons, you have the same number of gas particles, you have the same volume, and the particles have the same kinetic energy. Although their velocities are different, so are their masses. The helium molecules are twice as heavy as the hydrogen molecules, so they will be moving slower, but they have more mass behind them. So they still hit the walls of the container with the same amount of force. Their kinetic energies are the same, so the pressures that are created are the same. Next question. The temperatures of the gases in the two balloons are? They would be the same because they're in the same place. You're holding both of these balloons. They're probably the same temperature. The number of moles of gas in the two balloons are? The same. This is called Avogadro's principle, which says that under the same conditions, equal volumes of gas contain the same number of particles. That principle is ultimately how we were able to determine Avogadro's number. Amadeo Avogadro didn't come up with the number himself. He came up with the principle that under the same temperature and pressure, equal volumes of gas contain the same number of particles. And then by weighing them, you can figure out relative masses. So moles are the same. Also, if you consider the ideal gas law, if you solve for moles, moles equal pressure times volume over the gas constant times the temperature. Nowhere in there does it ask you which gas it is. The densities of the gas in the two balloons are different. Density equals mass over volume. Since you have the same number of particles in each balloon, but helium weighs twice as much as hydrogen, you're going to have twice the mass and the same amount of volume, so the density of the helium balloon is double that of the hydrogen balloon. Let's look at some more questions. In this one, we have a neon balloon that has double the volume of an argon balloon. And which one represents the mass ratio? So think about this. The answer is a 1-to-1 ratio, because even though neon has twice the volume and therefore twice the number of particles, argon has a molar mass that's twice that of neon. Argon atoms have a mass of 40 atomic mass units, whereas neon are only 20. So you have half as many particles, but they weigh twice as much, so you're going to have the same overall mass, essentially. This next one is a little bit confusing to understand what's happening, but we have a movable piston with some gas particles in it, and it's got nitrogen gas, and you have a piston that will move up and down so that it maintains a constant pressure of 6 atmospheres in here. In other words, there's a constant force being applied on the top of this piston of 6 atmospheres, but the piston can slide up and down and change the volume. Initially, you're at 45 degrees Celsius, your volume is 6 liters. You then cool it down. So think, what will cooling it down do? Well, it should lower the average kinetic energy, meaning these particles will move more slowly, so they will stop hitting the walls of the container and therefore the bottom side of that piston as hard. When they stop pushing up as hard while you're applying the same amount of force downward, that piston is going to slide downward in that cylinder until the collisions equal that 6 atmospheres again. So which best explains the final result once the gas sample is cooled? Well, the answer is, think about it for a second. The answer is D. The volume will decrease. The pressure will remain the same because that piston will move downward until the pressure comes up to equal 6 atmospheres again. But in doing so, the volume has decreased. So we have the particles are applying less force, but it's over a smaller area, and pressure is force over area. So you get the pressure to be that same 6 atmospheres again. All right, so that was some concept checks. Now we've got a new topic to talk about, although it's not really new. We've been discussing this quite a bit. Vapor pressure is the pressure exerted by the vapor from its liquid at an equilibrium. In other words, when evaporation and condensation are occurring at similar rates. Vapor pressure increases significantly with temperature. In other words, the higher the temperature, the more vapor you'll have above a liquid. You may notice, for instance, as you're heating a pot of water over the stove, as the water gets hotter, you start seeing more and more and more and more steam start coming off of the container. Now, for vapor pressure to be measured, we have to reach equilibrium, so it'd have to be a sealed container. But that's what that is. Solids can also have a vapor pressure through sublimation, where it goes directly from solid to gas. But when the vapor pressure of a liquid equals the atmospheric pressure, the liquid will boil. So you can boil a liquid by heating the temperature up until the vapor pressure reaches atmospheric pressure, or you can lower the atmospheric pressure until it equals the vapor pressure at whatever temperature you're at. If you get the pressure low enough, you can cause water to boil at room temperature. It's still roughly 20 degrees Celsius, but it's boiling. As you go up in altitude, atmospheric pressure decreases. So at high altitudes, if you're, say, mountain climbing, for instance, you're at a lower atmospheric pressure, so water will boil at a lower temperature, which has some significant impact on cooking. If you're trying to cook rice or pasta, or anything else you're cooking in boiling water, you have to cook it for longer because you're at a lower temperature with that boiling water. It's no longer 100 degrees Celsius. On the other hand, if you're baking something in the oven, you need to add more moisture and cook things for a shorter time, because at those temperatures in the oven at lower pressure, the moisture will escape and turn into a vapor much more rapidly. And so if you just bake a cake using regular directions at very high altitudes, you're going to end up with some very dry cake as a result. This shows how this equilibrium is established. The water vapor will start to evaporate, and then, or whatever liquid it is, and then it will also start condensing, and eventually that starts happening at the same rate. And so you measure the partial pressure of that liquid. That's your vapor pressure. This kind of shows if you start with the liquid put into the container, it evaporates at a constant rate. Obviously, when none of it has evaporated yet, you can't have any condensation. But the condensation rate will increase until you reach equilibrium. And we don't need to look at this one yet. This shows vapor pressure of several different substances: diethyl ether, ethanol, and water. You can also see that the point at which it equals atmospheric pressure, 760 torr, that would be its boiling point. Water at 100 degrees Celsius, ethanol at 78.4 degrees Celsius, diethyl ether at 34.6. The last thing we got with this is collecting gases over water. We've talked about this if you've done the lab. For those of you in cohort C, you'll be doing this lab on Tuesday. But when collecting a gas over water, the partial pressure of the water vapor has to be subtracted from the total pressure in the container. This is an application of Dalton's law. And the vapor pressure of water, as we just saw on that last slide, varies directly with temperature, and you can look that up in a table. Right. Now, you have to be careful with collecting gases over water. You can collect hydrogen gas over water, for instance, or oxygen gas or nitrogen. You cannot collect carbon dioxide gas over water or any other gas that is water soluble. You would not want to collect ammonia gas over water because NH3 is going to hydrogen bond with the water molecules. It's incredibly soluble. Carbon dioxide actually reacts with the water to form carbonic acid. So any gas that reacts with water, you don't want to collect it over water because you're not going to collect the gas quantitatively. You're not going to get all of it. Hydrogen gas, which is completely nonpolar, it doesn't dissolve hardly at all in water. So it's a great one to collect over water. Right? And this is kind of leading into what we're going to talk about next week, which is solutions when you mix things into water.